Hello, welcome to another Saturday session of the John Chappell Natural Philosophy Society. And today's talk will be from Franlkin, who about dark matter using ChatGPT. ChatGPT is AI, which is artificial intelligence, and I think the results he gets is similar to what I get. The issue of Newtonian physics is the only teach a dumbed down version of Newtonian physics, and so a more complicated version will bring in extra things. So it could be that dark matter can be explained by a more complicated version of Newtonian physics, and I think that's it's my opinion of what Franklin Hugh is bringing up. So if we can now, let's go over to Franklin Hugh's talk. Thank you.
All right, so thank you, Roger. And yes, today we're going to be talking about ChatGPT. So I'm going to bring up my presentation here. And let's see whether I can do it this way. Okay, no, not that way. We've got us, we've got you, we've got the presentation, and we've got that. Okay, so I think we'll start this way. And so this video is also on YouTube. Unfortunately, it was a 50-minute video, and I'm not really going to go over that again. But if you'd like to go see that presentation, the long presentation, you can go check that out. But my plan here is to just go over things fairly quickly, because the main idea here isn't really that complicated, really. What we have is that we have this rotation curve, and it's always this picture for some reason, of the rotation curve, where we see that we observe that the stars accelerate or are flat the further you get out from the galaxy, but people are expecting the star velocities to slow down because gravity gets weaker as you get away from the core, of course. So the problem with that, I believe, is that we have this gravity formula here, and this is F equals, mass divided by the r squared. And but actually, the original universal gravitational law is actually the mass over the distance from the center. So the difference here is distance, not radius. You have radius in the first section here, and but you have a distance. Now, the way you can think about this is that suppose you were sitting at the top of the Giza pyramid in Egypt. So how would you calculate the force of gravity of the pyramid on you standing on top? And then you would struggle to use this top formula here, because what on earth would you use for radius? A pyramid does not have any kind of radius, right? Really, the only way you could do it is by manually calculating the force of gravity between the block you're standing on and you, and then do the same thing for every other block in the pyramid, and then add it all up, and then you would be able to find out what the force of gravity is. So this is something that Newton came up with. In the case of a sphere, this formula works over r squared. But in the case of anything else, like a pyramid or a disk, it just doesn't, because you do have to still do this whole manual adding up every single force from every little bit. And Newton did that for a sphere and came up with the answer that it looks exactly like the regular gravity formula, which I think would have been just super frustrating for Newton to come up with this very complex thing about making up the Earth as a ring and then as a disk and then adding up spheres, just to come up with something that looks practically identical. So, I think that maybe astronomers, it could be understood why they mistook this for the universal law of gravity, even though it's not. It only applies to spheres. And, this was first noted by David de Hilster in his paper. And he has his own video here, Newton trumps over dark matter. And that's kind of what triggered this whole subject for me, in that, that's very interesting that we have these spherical galaxies and they don't have this dark matter anomaly, right? So I think this was proving that the mainstream was using, the sphere. I call it the spherical gravity law, for lack of a better way of saying it. And let me just go full screen on my presentation here. And but the problem is, so I wanted to go beyond that, because there wasn't a whole lot of reference papers or other things. So I went beyond that and I found additional evidence, and that's in the form of 6 other galaxies which don't have any dark matter in them. So, and there are actually pictures of these galaxies in the references here. And while I am no expert here, and while these pictures were not specifically noted to be spherical, these were just noted as having no dark gravity in them. That these are certainly, they're not flat disks. They all seem to be very diffuse galaxies, which seem to have, generally circular kind of distributions on them. So, but this is really a very important piece of information that's going on here. And let me see what is going on with this. Okay. Just a moment here. Because a galaxy that doesn't have any dark matter is really a huge monkey wrench for both the dark matter postulate and even its alternatives. So they try to explain it in like certain galaxies that may have been stripped of their dark matter. But, generally speaking, even the researchers who have looked at this are very puzzled, because, they looked at all these possible things that they could have done, like adjusting the parameters or alternatives to general relativity. But, but there are none. And in the most repeated galaxy formation framework, the so-called cold dark matter model, we would have to introduce extreme parameter values that are far beyond the usual range. Also, with modified Newtonian dynamics and an alternative theory to cold dark matter, we cannot produce the motions of the gas within the galaxy. So this is a major problem for MOND, because MOND presumes that at the low galaxy rotation speeds, like out in the distance, that the gravity formula becomes modified. However, if you find a galaxy which absolutely has no dark matter at all, that would contradict MOND, because MOND would predict that every galaxy which has slow rotation, curves out in the edge, would have dark matter. So these 6 galaxies with no dark matter are a complete contradiction to the modified gravity theory. And the other problem is that due to the cosmological models, if there's no dark matter in these galaxies, they shouldn't have formed in the first place. So that is another huge monkey wrench for the whole dark matter theory. So the alternative which is left is, as David de Hilster was surmising, is that just the gravity law has been not correctly applied to disk galaxies. It's not that we don't understand how gravity works or that there is some modification to gravity, but rather we're just not applying it correctly. So this is where I started to also look to see whether ChatGPT could help out in this problem here. And so you can just ask it, you know, to plot you this thing. And, you know, it tries, and I was kind of stumbling along, and it actually comes up with a Python program. And maybe later on, I'll show you exactly how it does this. And then you can put that in Python anywhere. And then lo and behold, I got this curve here that you can see here. And as you can see, it is totally flat. And it would go flat, you know, basically out to infinity, right? Now, I was very surprised about this. I mean, I was not expecting this, really. But somehow I fooled ChatGPT into coming up with a curve that seems to very closely match the observed galaxy curves. So, ta-da, ChatGPT produces flat gravity curve, and everyone probably thought that the title of my YouTube video was clickbait, which it kind of was. But nonetheless, somehow it got the right answer, right? So, of course, everyone is totally skeptical about ChatGPT, and certainly we can discuss that. And, you know, I noticed, and other people noticed, that ChatGPT actually got it presented this formula to the right here, but it actually came up with this code, which is actually not the same thing. You know, it actually is missing this division by R term. So it made a mistake, right? So ChatGPT screwed up, but somehow got the right answer, right? So it screwed up, it got the right answer. And what I did is I reverse engineered it and found that what it was doing is that it was treating the gravity as being proportional to 1 over R, which curiously enough is the same thing that Mond kind of proposes. So there was this recent video by Sabine Hassenfesser where we have this other piece of evidence, which is really bad for the dark matter theory, in that the galaxy curves are flat to like way beyond where we would expect dark matter to end. And the one theory that does predict that is Mond, which basically says that the force is proportional to 1 over R, not over 1 over R squared, which is basically what Mond was predicting, except that Mond is kind of negated and disproven by the existence of these 6 galaxies that don't have any dark matter in them. So I would be kind of curious to know what the Mond people think of the 6 galaxies that don't have any dark matter in them. So, but to go beyond that, so we have a lot of evidence against dark matter now, the recent data. But what do other scientists think? Now, you can go and you can search the internet, and you can find several other researchers who agree with this particular viewpoint that you cannot treat a disk like a sphere, right? So I have a diagram here of one of the papers here. And so the orange line is what they are getting as their Newtonian prediction. And then they have the blue line, which is what the observed. And the actual, shape of the curves match up almost exactly. If you were to move this orange line directly over this blue line, you would see that it matches almost perfectly. Even the subtleties, and like there's a little dip here and a little dip there, even those would match up. The only difference is that they get the velocity wrong by about 100 kilometers per second. But there might be some reason for that. But what's interesting is that when you treat the galaxy as a disk and you apply manual numerical methods to calculate what the gravity should be, you can get it correct. And there's another guy who did similar thing, and this is actually matches the M33 galaxy in this typical picture here. And he almost got the galaxy curve exact, right? So there's several examples of people doing this, calculating, not trying to cheat, not using the spherical gravity law, but actually going and breaking the galaxy up into like little blocks, just like I explained with how you'd figure out what the gravity would be to the Pyramid of Giza, and then figuring out what the velocity would be, and lo and behold, it matches, right? And to help motivate that, why does gravity, the force of gravity, change? And you may not know this, but that the force of gravity is 1 over r squared when you're considering points which are far outside of the actual mass. So this is why this works in our solar system, because the solar system, most of the mass is in the sun, and everything that's orbiting is way past the mass of the sun. So that works. But what is less known is that Newton also came up with another gravity theorem, which says that, say, if you are inside the Earth, you would find that the force of gravity from the center to the outside increases linearly, is what happens there. So when you're inside a gravity mass, then your force of gravity increases linearly, rather than 1 over r squared. Now, this particular paper that I have noted here, basically said that we could treat it that way. So, but I'm not sure that you can, but it does match up with, ChatGPT's presumption that the gravity is, a 1 over r. It's a linear type of force rather than an r squared type of force. But this is what is the basic crux of the problem, is that when you're looking at a galaxy, you are looking inside a sphere, not outside a sphere. And that is the major difference. So the form of gravity changes completely between those two geometries. Of course, the main question I get when I tell people this is that, oh yeah, okay, so only Franklin knows this, and he's smarter than 10,000 astrophysicists, and 10,000 astrophysicists can't possibly be wrong. That is the point in this is another quote from the paper that I had there. It says that physicists and astronomers aren't totally incompetent. The evidence for dark matter that comes from the rotation curves of galaxies, which by the way, is far from the only evidence there is not based upon assuming that K3 holds with the Keplerian or Newtonian gravity. The expected orbital speeds given the matter we can see are based on Newtonian gravity, with perhaps some small corrections from Einstein's, not Kepler's laws. So, we have this really hard to understand situation where I think that clearly any legitimate astrophysicist would not disagree that using the spherical gravity law on disks is not terribly appropriate, but that seems to be what the case is. So, and the giveaway is the shape of the curve. So if you ask ChatGPT straight up without trying to confuse it, do a orbital velocity curve, it comes up with exactly that same shape curve as seen in the atypical dark matter picture here. And that shape of the curve gives away what they're using. So they're using this formula. Anytime you see something divided by r, then you know that they're using the spherical gravity law, which is wrong, right? So, like I said, I could be wrong. And so I have these questions about, whether the 6 galaxies really have spherical symmetry, or can you find me any spherically symmetric spherically symmetric galaxy that actually has dark matter in it, right? If you can find one of those guys, then you would refute this hypothesis, right? But I'm guessing probably not. And, or, if you brute force calculate the force of gravity between every star, which I think those other 2 papers I presented did, that you will get what is the observed what is the observed rotation curves? But so that's the end of my presentation, but I'd also like to just take a moment to bring up our special guest star here, which is ChatGPT. So here's ChatGPT, and let me see if I can make this any bigger here. But hopefully you can see that. But you know, you can start out by asking, can you plot the velocity of the galaxy with a simple flat and thin disk that decreases exponentially? So if you ask it straight out, you know, it'll come up with the formula for the plot and the gravity here. And see, so it's using this GM over R divided by R. This simplification is using the spherical gravity law. And actually now, ChatGPT can actually go ahead and plot the thing for you. But we can also ask it to do different situations, like can you plot the galaxies if it were a simple flat and thin disk? So instead of being exponential, this is just a disk of consistent density that just goes out. And curiously enough, if you do that, then you see that the rotation curve is just an increasing linear curve there. So that's interesting, right? So definitely if your disk just keeps on going out, and this is kind of like if you were in the center of the Earth going out, that the expected velocity is just rises linearly as you go further out. But then if you ask it to assume the mass decreases exponentially, then you see it comes up with this curve, but this is wrong because the velocity should be 0. So you can fool it, you can tell it, say, but the velocity should be 0 at 0 radius, and then it agrees, yes, you're right. So it makes a correction, and then it goes and makes a correction. So, but then I ran out of, I don't know, it stopped doing the plots for me, but it went ahead and will go ahead and generate, in fact, all of this Python code. So I wanted to show you how you can execute that. So you copy that, and then we go to this is a program called Python Anywhere. And so what I do is I paste that code into here. Let's see, did I do too much? Let's see here. And then I run it. Yeah, no one can read that, and I really don't expect you to. So, but it's just a demonstration here. So you run it, it generates the plot. Then you can then view you have to download the file, and then you can then view the actual, oops, just a second here. Having a problem moving it into the screen there. Then you can view the actual chart that it generates. Okay, so I think that generally does it for my presentation. And so I'm going to bring up Roger here again. Roger, you there? You seem to have turned off your camera there.
Hi.
Oh, there you are, right?
Hi. Thank you.
So I'd like to open it up for questions.
Okay.
Questions, comments.
So can I first present my screen? My screen down the bottom there. Add to it. Yeah, that's it. So I had Amaret who wanted to point out he had a paper on it about dark matter and dark energy. Right. Can we roll down? So that's the abstract for it. So various people have had a go at this. dark matter issue from the dissident community, not just the mainstream. But can I bring up my other screen? Close that one down. Stop screen. Present. Share screen. Text share. Does that come up? Can put up the next one. Can you put the next one, please?
Let's see. Did you somehow take down your presentation?
That's it.
That one.
Yeah.
Okay.
So according to my researches on this subject, what was happening with Newtonian physics before Einstein is they were coming up with a unified theory, which was called the vortex theory. And when Einstein came along, they sort of abandoned that. So they don't teach this anymore at university. They sort of they teach Newtonian physics, but they don't get to when it starts getting complicated. So it's sort of like a dumbed down version of Newtonian physics. And so everything's sort of with this 1 over r squared thing version of Newton's gravity, that seems to be what they teach, but they don't want to then go on to the complications that come after that, and which got abandoned by them as being looked at because of what Einstein did with his relativity and then the quantum revolution. So basically, physics students, I think, are being shortchanged here. They're not given a proper grounding in Newtonian physics, and that's pretty much standard across the education system. And so if that's the case, then maybe these physicists that are coming later are not understanding how complicated Newtonian physics really is, and then are misapplying it to things and coming up with these things like dark matter and dark energy. So that was the point I wanted to raise. But also, Harry Ricker wanted to give a little short talk following on from what you were saying, Franlkin. I think he was not agreeing with what you were saying, and he wanted to give his point of view on it. Is he there in the green room?
No, Harry's not here, although I think he brings up the point that, as I mentioned, there are actually a lot of other reasons for believing that dark matter exists. And so one of those is the most accepted theory of the cosmos is the lambda cold dark matter model.
Yeah.
So that's what Harry wants to mention, in that they need dark matter in order to explain galaxy formation. So, even if there was no evidence for the galactic rotation spirals, right? Let's suppose that got completely thrown out, right? Say, oh yeah, well, we just calculated it wrong. You'd still have the whole problem of how do you explain galaxy formation, which is another problem. I mean, perhaps I'll go ahead and I'll bring up, there's a video here from Angela Collier, and she mentions, let's see here, let me go ahead and add that to the thing here. Okay, so we have Angela Collier's video here, and there are three kinds of evidences that are given. So one of them, is the galaxy rotation problem there. And I have a comment in there saying that this depends upon the galaxy being spherically distributed, and they're not. So that is how I refute the galaxy rotation problem. The other problem is the CMBR proof.
I think it's a bit spool that those slides.
Yeah, well, I don't expect anybody to read any of this, right? So
Yeah, okay.
this is just, there's Angela. She's got this video. Dark matter is not a theory. If you got 43 minutes, you can watch it. But she gives the three main evidences for dark matter, and this CMBR proof. So you might actually want to watch this one. So the CMBR proof is based upon this. You can see there's this red curve here. So, based upon this sky map of the CMBR, they're saying that there's some power fluctuations depending on the angles you see on the chart in the thing here. But, this looks like someone just threw up some paint on a wall. But they get this particular curve here. Yeah. And what you can do is that you can change. We have down here the universe content. So if you just mess around with the theory and try and make this curve match up with the observed here, you can try and let's see here. So it can't be. And if you're wondering where is this that statistic where they say that there's the universe consists of only 5% real matter and dark matter, and dark matter consists of like 26%. Well, that's just a matter of adjusting these 6 parameters in exactly the right way to come up with the matching power function. So ta-da! So somehow this proves that dark matter exists, right? But really, this is called typically called curve matching, right? So you come up with a theory which has these 3 things: atoms, cold dark matter, and dark energy. So you make up your theory. Then now this is a matter, I don't know if this was a post-diction or a prediction, but if the researchers knew about this curve before they came up with their theory, then they could have made their theory just match that curve theory. They knew what they were looking for, so they made a theory that might produce this and had cold dark matter and dark energy in it. And when you adjusted it just right, then you could come up with what they observed. But like I said, this is called curve fitting, where you have enough parameters where you can adjust things so that you can force it to fit, right? So I see Harry's here, so I'd be kind of curious to see Harry. This I think is what you were talking about as being a tautology with cold dark matter. Are you there, Harry? In that basically they're assuming that this stuff is true, and then they go and they say, aha, we made a match, and it's like, well, it's not very impressive that you just designed something to match that curve. So that is the CMBR evidence. And then finally, let's see, I have a bunch of comments in here. Where's my other comment? Yeah, and there are lots of comments in here from other people, and I don't expect you to read any of that. So, but it's interesting just going over those comments. Let me bring this down. But the one thing that we do have here is the bullet cluster. So the bullet cluster is given as another evidence of the CMBR, and she explains that we see that the dark matter is supposed to be non-interacting. So we find that we have 2 lumps of dark matter on the left-hand side and the dark matter on the right-hand side. So they pass through each other. And so that proves that there must be dark matter somehow. Although she also goes on to explain that the stars also do exactly the same thing. The stars pass directly through each other. And so if and these are clusters of galaxies, and what do galaxies have in the middle of them? You know, black holes, which are pretty black to us. So why couldn't it just be ordinary matter that's passing through the bullet cluster? You know, if stars themselves can do the same thing. So that is how I explain away the bullet cluster as being evidence for dark matter. But you know, once again, the curious thing is how could all of these how can 10,000 astrophysicists be wrong? How could they have spent, you know, literally billions of dollars coming up with all of these dark matter searches? So we do have some, you know, some questions here. So I know that let's see here. That Quest was asking, you know, whether I came up with this on my own, and no, quite clearly not. You know, I was originally just looking at David the Hilster's video, and then was inspired to see, well, what else do we know about this, and tried to look at the various resources, and eventually ended up going on ChatGPT, because what I was really trying to do is that I was really trying to find where this original slide comes from. What is, you know, in this slide here, then this is always the slide that is shown for dark matter, you know. And how do they calculate this expected from the visible disk thing? You know, where does that curve come from? And that is really hard to find. And so I had ChatGPT come up with it. But so we have a few people in the chat room here. Would James, do you have any comments you'd like to make?
What, me? Well, as I said, I think it's the mainstream haven't got a proper understanding of Newtonian physics, so they've not been taught it properly. They've only got a dumbed down version of it, so hence going wrong.
Yeah, but do you think it could be as simple as them, you know, mistaking the spherical gravity law for the universal one, right?
Yeah, I think it could be, because they don't get taught that. They only just get taught the inverse square law. They don't seem to go into the reasons for the inverse square law, and then hence for the reasons for why you need to modify it under other conditions. So, and there's no experts in advanced Newtonian physics anymore, I don't think. It's sort of like everybody's gone diverted onto other things such as quantum physics and relativity and thermodynamics and lots of other things like that. And Newtonian physics is considered old hat, so they're not getting the professionals looking at that. As I said, it's what the Newtonian physics led to was this vortex theory, and the vortex theory created lots of problems in trying to work it out, and so eventually it was abandoned, and they just treat that as the theory as being wrong, because then Einstein brought all his things in. They decide, oh, the vortex theory is wrong, and we just go with what Einstein says, and so there's nobody been working on the vortex theory anymore.
So the vortex theory, how is that related?
Well, the vortex, what you had in the idea of Newtonian physics, you had to come up with a unified theory. And in the 19th century, the idea for the unified theory of everything was called the vortex theory, and it was advocated by, I get confused a bit by the name. I think it's Lord Kelvin. Yes, Lord Kelvin, also called William Thomson. And so he was the main person promoting that. And then when Einstein came along, it all got abandoned. So it's the defect in the education system. They don't teach physics properly. They don't teach the history of physics properly, and hence they're not doing the physics properly. They're not realizing there's a big gap between Newton and Einstein, and they're not teaching that big gap anymore. So it's a big lack of their knowledge base. And that's sort of like one of the things I've been trying to point out. That's how dumb they are. And the education system is standardized, so they teach the same, try to teach the same physics everywhere in the world, basically. Sort of go to the Soviet Union, I think they're just copying what the West is doing for the standard physics education. So everybody's getting the same version of physics, and so that with a big gap in it, they're not being diverse in their teaching of physics.
Astrophysicists who should know everything about how to apply gravity continue to apply it incorrectly. I mean, I could understand, us, amateurs, not knowing about how to apply gravity and using 1/r squared. But how could some learned professor who spent like $1 billion on a WIMP search not know that you can't apply gravity that way? See, that's what I find hard to believe. And
well, they're not taught. They're not taught it. It's sort of like Einstein came along, and it's supposed to be everything's changed. So hence they're not going into as much detail into Newtonian physics anymore. They're sort of like lost wisdom.
That's no excuse for someone who's spending billions of dollars. That cannot be. I mean, like I said, it's obvious that 1/r squared isn't going to work. Like the other example I give, that like suppose you drill a hole into the center of the Earth, and then you predict what the force of gravity would be at the center of the Earth using 1/r squared. So your radius is going to be 0 or close to 0. So your force of gravity at the center of the Earth should be infinite, right? Well, that answer is
supposed to be 0.
So that can't possibly be the universal law of gravity. It gets that particular situation wrong. That is why I showed that example that if you are inside the Earth, the gravity rises linearly with the distance. So at the center, where r is equal to 0, the force of gravity is 0, as you would expect. And it goes to a maximum as you go out to the surface. And then from there, once you leave the surface, then it decreases as of 1/r squared. And this is another way I try to explain this to people, which is that if you're talking about you're in the galaxy disk, and you have matter, that as you go further out, the amount of matter that's enclosed within the circle is actually always constantly increasing. Even if the surface density is decreasing, still the amount of matter enclosed in any radius as you go further out of a galaxy is constantly increasing. So the gravity is increasing as the further you go out. So you would expect it to either go faster, as I had shown in that if you just have a flat thin disk that doesn't decrease, the rotation rate actually increases because there's just simply more gravity. It's like if you were on say the moon, and then you just pile matter up until you got a bigger moon, then that would increase the amount of gravity. And if you increased it more, you would get more gravity. And that's how you think that it increases linearly. The other thing I was reading about is that it's not 100% clear, how much mass is out there in the areas you cannot see. I mean, it's not glowing, but certainly there's hydrogen gas out there. But because the area outside is so much larger, that can still include a significant amount of mass. I think some of the estimations were that the area that you cannot see, may contain 2 to 3 times the amount of mass as, say, in the galactic core, right? So that doesn't mean that it's just because it's not a visible star that it's not there.
Yeah.
Although people have, made pretty accurate calculations. Like I found another paper just yesterday where they carefully modeled every single galaxy, like I said, using numerical methods, and matched these 47 galaxies up almost perfectly to their observed rotational curves. So once again, the point being, it's not that we don't understand how gravity works, it's that we have simply misapplied the universal law of gravity by trying to use these cheats, right?
Yeah.
If you don't cheat, if you go and, I think a computer should be able to go and map out every single star in a galaxy and then painstakingly calculate the force of gravity to every other star in the galaxy. And then you can calculate what the expected velocity is correctly. So, but I do see we do have some interesting comments here today. So, Questing also apparently was doing the same thing I was doing, which is that you can use it to kind of help understand the mainstream understanding of dark matter and actually come up with some of the flaws that may be there. But in my case, I kind of fooled it into doing the wrong thing. I'm still not quite 100% sure how I did it. I kind of walked it down the garden path, and then it came up with that flat curve, which I think is correct. And so he also brings up he didn't know that there were these spherical galaxies. Yeah, I mean that's really interesting that we have these galaxies which do not look like the typical flat disk. The one that David de Hilster was showing was literally like a diffuse ball, right? And so apparently there's, I don't know how many of them there are like that, but so far they've found at least 6 of them.
So I don't know how well the theory is now, but it was a theory that all galaxies are supposed to be spherical, and it's when these galaxies have had near collisions that they've made them squirrel round like what we see the Milky Way as. So that's the result of near collisions. I don't know if that theory is still believed, but that's one of the things I heard a long time ago.
Well, that's certainly a possibility.
There's a lot of mysteries.
This discussion, it's like, well, those galaxies should have dark matter in them, right? And that's a really big problem for both modified gravity and the dark matter theory, that if those galaxies don't have dark matter in them, then there's something wrong. That's why I think it's important to trying to find as many of these as you can, and see if you can find one which has the dark matter in it. You would think the ones that have the dark matter in it would actually be more common. So, but if it's not, then it's telling you that whatever algorithm you're using to try and figure out what the Newtonian gravity is, it's somehow sensitive to the spherical distribution, right? Because when I keep on asking ChatGPT about this more and more, it comes up with a very complicated integral for what the gravity force should be, and it draws another curve which doesn't match anything. But no matter however they're getting it, they're apparently not getting it correct, right? So I think rather than making up this idea that there must be some strange dark matter, I think it's far or that we don't understand how gravity works and somehow it becomes different in different regimes. I think it's probably far more likely that we're just doing the calculations wrong, because the calculations themselves are very complicated, right? You can try and come up with approximations. mean, it's so difficult that that's all you can really do is come up with approximations. And that's why when people go and try and apply it properly to a disk galaxy by like breaking it up into little blocks and figuring out what the gravitational attraction of every block to every other block is, that you can replicate the actual rotational curves.
Okay.
So we've got another question. Questions have got a lot. So does he mean that the principle in question would apply to spherical galaxies the same way it applies to spherical celestial objects such as planets and stars? Well, actually, I would be implying probably the opposite of that, in that gravity, when you're applying it to spherical galaxies, well, the thing is that a spherical galaxy does have the spherical symmetry. And because it does, then it will obey the 1 over r squared principle. So in that way, then it would apply to, you're talking about celestial objects such as planets and the stars. So, and in that, we expect the velocities to decrease as the further you go out. And so, well, in this case, yes, I think I would have to say that the principle would apply both to spherical galaxies and it's not really a spherical celestial object, but rather a system which has a central mass, is what that is. So although the spherical galaxy is not really a system with a central mass, so I myself still have questions about how that works exactly, but apparently, since there is no observation of dark matter, that the outer stars in that spherical galaxy are rotating slower according to Newtonian and or Kepler's laws, unlike the flat ones where it's pretty much flat. And the new finding that blows away dark matter is that they are flat out to like millions of kiloparsecs, which is way beyond where the dark matter should stop, because the dark matter halo cannot be everywhere. So it must stop, and then we would expect to see at some point it should decrease, but we don't observe that decrease. So not unless the dark matter halo goes out to like forever, they can't do that. But they can't say that goes out to forever, because then their cosmological models wouldn't work. So that's referring to that quote I had in my video there about, not fitting the model. And we have some other.
Do you see a comment here that somebody's having problems with StreamYard?
Yeah, people are always having problems.
3:30. Somehow, reason his computer wouldn't stay connected to StreamYard. So it wasn't just me having problems with StreamYard.
Usually that's a problem with your computer.
Yeah. The
stay connected.
StreamYard seems to have. I've had a lot of problems with StreamYard. So if you're having problems with StreamYard, you seem to have to go to the YouTube version and watch it from there.
Let's see here, but although that's from someone who has admin access.
Yeah.
What comment do we have here? We have central volume with the black hole.
It's working now, but it wasn't working earlier.
Okay, was that you?
Oh, we have Harry.
Harry, are you having problems with StreamYard?
Well, good to have you here, Harry.
Yes, it wasn't working, but after I reconnected it, it wasn't working, but after I reconnected it a couple of times, it's working now, sort of.
Okay.
I'm confused, Franklin, as to just what the bottom line is for what you're talking about.
The bottom line is that
What's the bottom line?
The bottom line is that if we just apply real universal Newtonian gravity to the disk in its shape, that we recover the rotation curves that observe. So the bottom line is we don't need modified gravity. We don't need dark matter. We just need to apply the Newtonian gravity law correctly. That's the bottom line.
So to me, it's puzzling. I mean, I have to go with the argument that the critics are saying, which is, I mean, you're just saying that astronomers are dumb people and don't know how to do astronomy. That doesn't really compute to me.
Yes, that is the main. That's the main puzzle. You'd think they'd know.
Well, that doesn't seem plausible.
Well, yes. I mean, I would agree that it doesn't seem plausible.
I mean, they've been working on this problem now
I mean, this is a simple mistake. I mean, simple. You know, a fifth grader should be able to see that you can't apply the.
They've been working on this problem for 40 years or more,
yes,
probably 50 years.
For 40 years or more, they seem to, I mean, literally in the literature, they say, I mean, I found a quote today which says that, well, for simplification purposes, we can treat a disk galaxy as if it were a sphere to the first order. And yeah, they say stuff like that, but no, you cannot treat a disk galaxy like a spherical object. Period. Right? It's
well,
just.
I agree with Stephen Gift. I think that you need to actually look at what the, you know, Stephen Gift has a comment. Did you see his comment?
Not yet. Let's see. What did he say? If you've got it, you can put it up.
He says you need to read the papers where they do the calculations.
Yes, I have read the papers where they try and do the calculations. Like I said, that is one of the hardest things to find.
That's not the impression I get.
In fact, I found the actual source code, I believe, that they used to calculate that M33 galaxy, and it is some very weird integration. But but eventually, you know, they come up with that standard picture with the expected Newtonian with it dropping off. And if they do that, then they're using the spherical gravity law, because that is the shape of the spherical gravity law formula, right? It's fairly characteristic. It matches exactly.
I don't know what you mean by First off, I don't know what you mean by spherical gravity law. It's 1/r². Is that what you mean by spherical gravity law?
That only applies to spherical mass distributions. That's not the universal law of gravity. That's a main point.
So your claim is that the law of gravity only applies to spherical mass distributions. It seems to be your claim, basically.
For example, Harry, so use that formula if you're standing on the pyramid of Giza, you know, the Great Pyramid of Giza, calculate using that formula the force of gravity of the pyramid on you standing on top of it. How would you use that?
I have no idea what you're talking about or why you're bringing up the Pyramid of Giza. But
because I want you to calculate the force of gravity of the Pyramid of Giza on you. How would you do it?
Well, you're saying, as I understand it, you know, I'm trying to get to the point of what your point is. You're saying that the 1/r² law of gravity is incorrect, right? Wrong?
It's only correct for spherical objects, and you are outside that the mass of that sphere. That's the only time it applies. Because you can calculate, if you have like a pyramid shape and you're standing on it, you can calculate the force of gravity that pyramid is exerting on you, correct? You should be able to do that, right? Right, Harry? Think about it. This is very important. You have something the shape of a pyramid. You are standing at the vertex.
According to physicists, yes.
Think about it. How do you calculate that? What's the radius?
Well, there's a lot of issues here, and I have no idea why you're talking about pyramids.
Well, that's
What
a
does that
key
got to
point
do
here.
with the subject at
That's a
hand?
key point here, because a pyramid is not a sphere, right? If I ask you to calculate, let's suppose you're out in
Well,
space.
you've already established that you claim that the law of gravity is wrong because of something about spheres, which I don't quite grasp.
Well, that's why I need you to grasp it. Suppose you're in space, and suppose you encounter this pyramid shape out in space where there's no other gravity other than the gravity from that pyramid. And I want you to land a rover onto the vertex. And in order to do that, you have to calculate how much is the force of gravity between that pyramid and the spaceship. So that's a very practical problem, Harry. So how are you going to do it? Can you do it with
Use
the
Newton's law?
law of gravity? Think about it. This is very important.
Well, what I would do, I would assume the traditional way of solving that problem would be to take divide the pyramid up into a bunch of mass segments, small little pieces, as they do in the calculus, and then calculate the force for each segment of mass or mass element, and calculate Newton's law based on each mass element.
Yes, that's absolutely correct. Okay, so that is the proper way to use.
I'm assuming that's what they've done for these spiral galaxies.
No, that is not what they've done. What they've done is that they've simply see, oh, it's a circle, it's got a radius, so let's just go.
Well, we don't know that yet. That's the issue that seems to be under discussion. And I mean, I've seen I don't know how they're doing the calculations, so I can't really speak up and defend them. So the question is, you need to show to us that they're doing the calculations wrong, and I don't really see that's happened here yet.
Well, if you look in any of the standard YouTube videos, which are meant for amateurs, blah blah blah, that's exactly the way they'll do it. They'll on one side they'll have the centripetal force formula, on the other side they'll have the gravitational formula, and then when you solve for velocity, you get gm divided by r, and that is when you plot that out, then you get the standard decreasing curve that you see in the standard picture. For that standard picture, that is definitely using the assumption that gravity falls off 1 over r squared. That's definitely the case. Now, like I said, I tried to.
So, are you aware of the fact that for the Milky Way, there's no evidence there's dark matter in the Milky Way?
I wasn't aware of that. I mean, I'd be surprised if that were the case. I would expect the Milky Way to also have a dark matter anomaly, because it is a flat disk galaxy like Andromeda, and Andromeda, I think, was one of the first places the galaxy rotational curves were observed. So certainly that would be the case. But to address your point about, if people were to calculate it like as you described, you have to take every single segment and add them up for whatever shape there is, whether it's a pyramid, whether it's a rectangle, whether it's some weird blob. That's the proper way to do it. And people have done that. There are people who do agree with this viewpoint that it's just a miscalculation of how, instead of and then they've just taken the approximation and a shortcut to come up with the expected gravitational curves. Because this is frustrating, because you can find all kinds of information on how they come up with the observed curve, but when it comes to coming up with information for how they calculate the expected curve, that is really hard to dig. It's basically every paper you find, it's just presumed a priori that the dark matter is there, and they speak as if always the dark matter is there. But I got it as far down as finding the source code for how they calculate the curve. And like I said, I didn't see it directly as the obvious GM over R to calculate velocity. Velocity was the result of some complicated integration, is what it was, which is probably closer to what the right answer is. But I asked ChatGPT to do the same thing, and I think it came up with a similar computation as like based on Bessler's. But I would still assert that whatever that came up with, it must still be incorrect, right? Even if they tried to do it the right way, even if they tried to calculate it as a disk, that if they're getting the decreasing velocity curve, that I would still assert that the chances are that they're doing it incorrectly, because when they apply exactly the same logic to these spherical galaxies, and this is the key, when they apply it to these spherical galaxies, they don't come up with any anomaly. It matches whatever algorithm they're using, right? Because this is the key. If we didn't have the spherical galaxy, then it's like, well, yeah, it could be anything. But the fact that we have these spherical galaxies throws a huge monkey wrench into the whole dark matter theory, because there's no way that galaxy could form if there's no dark matter in it. So that's why some of the explanations is that, oh, well, this dark matter was sucked out of this galaxy by this other nearby galaxy, which might be a possibility.
Well, you said that before, Franklin. Now, originally Zwicky deduced that there was a missing mass issue with clusters of galaxies, primarily the Virgo cluster of galaxies. How does your explanation explain that issue?
Well, it really doesn't, because I'm just explaining rotational galactic curves within a single galaxy, as opposed to clusters of many, many galaxies. That is something else. But it could be something similar to that, because once again, we're not talking about gravity created by a single point source like the sun, right? This is how they always explain it, that we would expect that the galaxies would behave such that the outer stars would rotate slowly, similarly to how the outer planets in our solar system are slower. They literally expect the same thing, even though the geometry is completely different, right? Like the solar system, 99% of the mass is located in the sun, right? And all the planets are located past the sun. A galaxy cluster, well, it's like 0% of the mass is located in the center of that. All the mass is located in this, cloud of galaxy clusters, right? And the thing is that the matter that's on the outside of an object like that matters a lot more than any central mass, right? So if all the mass, like if 3 times as much mass exists outside of the galactic core, that's going to make a much bigger difference. So you would expect that, the things on the outside will be moving a lot faster, because there is just a lot more mass inside their orbital radius. As you go out, this is the thing I'm trying to explain. As you go out in the disk-shaped galaxy, there might be 3 solar masses at this distance. There might be 10 solar masses at this distance. There'd be 15 solar. The further you go out, the more mass is included inside the orbit. And everything we know about gravity says that the more mass you have, the more gravity you have. And so we would expect faster rotational velocities. But I want to see, whether you kind of understand that, because you do make this main point that may not get it, that why is it that the 1 over r squared gravity law is misleading, in that it only applies to like situations like our solar system and doesn't apply to situations like pyramids or a disk with a bulge in the middle. It doesn't apply to those situations. Now, I know you also, Harry, you were also mentioning that you wanted to present something else. You know, we might let you just go ahead and do that if you'd like, because I think your concern is that there are a lot more evidence for dark matter other than, you know, the rotational curves. Even if you got rid of those, even if you got rid of that evidence, you'd still have to deal with this whole thing about how galaxies are formed, how space behaves. Is that what you were trying to get at, Harry?
Well, the issue is that this
I see
not working.
You cut out a little bit there.
The link is kind of degrading now.
You're kind of breaking up there. Now we do have a question from John Hodge here. That is the outer region of the graphs where the RC is flat is molecular hydrogen, and that is in fact true. That, you know, there's that mass out there, and some of the reference I've read are saying that actually the mass increases linearly as you go out, just like in the case of if you're inside the Earth and you walked your way out, that the gravity and the mass increases linearly. And so that is a possibility that even though it's just molecular hydrogen, is not glowing, that it is increasing the mass of the galaxy. And curiously enough, they now measure the rotation of that gas, like, and this is the new data, using gravitational lensing. So using gravitational lensing, they can see the gravity of this molecular hydrogen and come up with its speed and find out that its speed is constant, you know, as far as they can see, out to infinity, which is something that dark matter cannot do. Okay, Harry, we got you back. You there, Harry? I think your signal is strong again. Are you there, Harry?
It's coming and going.
Oh yeah, unfortunately, yeah. I think that maybe if you turned off your video feed, and so we just hear your audio, that would make it easier.
We'll talk about this of dark matter and where it comes from. It comes from cosmology, and it's needed to make the cosmological models work.
Yeah, so Andrew asks the obvious question here, is that aren't you aware that physicists take advanced courses in classical and Newtonian physics? And yes, that's why I'm still surprised.
I don't think that's going to change anything here. I don't know how. You can turn it off if you want.
They do. I've looked at those things, and they don't go advanced enough on those things. That they miss out things on vortex theory, which is I've mentioned. They miss all that out.
Yeah, so Harry, on the bottom of the screen, you should see stop cam on the lower left of your screen. So that should shut off your video feed, hopefully giving you more audio bandwidth. But the thing is that we have these physicists, they've taken advanced courses in classical and Newtonian physics, but yet still seem to insist on making statements that we can treat the disk galaxy as a sphere, which seems strange. And we all similarly have people who have taken these courses and know about that correctly apply Newtonian physics and are able to recover the galaxy rotation curves, right? So once again, in the case of the emperor has no clothes, right? In that, everybody is saying, oh, well, we believe this. The king says that he has clothes, so he must have clothes, even though, it takes the little boy who hasn't been, brainwashed to say, but wait, he's naked, right? And so we are now getting all of this new evidence that's contradicting dark matter, and these galaxies which have no dark matter in it is particularly vexing, right? It's like dark matter does not compute. It completely breaks their models that you have a galaxy that has no dark matter in it. That just doesn't. That breaks MOND, and that breaks the dark matter molecules. We also have this other evidence that Sabina has brought up, that these curves are flat out to forever, and that definitely contradicts the dark matter model.
Can you bring up my slide again, please? Sorry.
Okay, let's see here.
If it's the right one. No, it's the wrong one. Sorry. Just a minute. We move from stage, and I'll bring up the right one. Share screen. Hold on.
Okay, so Harry, you managed to turn off your camera. So can you?
Sure.
Is it
This
better
one.
for you?
There you go. That's the one I want. Can you put the one? That's it. So this is the vortex atom. This is the Victorian theory of everything I was talking about. It's from the 19th century. And I've talked to the person who's written this paper. I don't know how to pronounce his name properly. It's Krag. And he's a historian of physics. And what happens is if you're dealing with things like that, it's just consigned to the history of physics and ignored by working physicists. So that's what he's pointing out, what he pointed out to me. You've got lots of Newtonian physics stuff, theorizing from different models and so forth, and it's just ignored because the working physicists think it's in terms of Einstein's relativity. So they're not really going into the advanced side of Newtonian physics, where you are speculating about lots of other things. That's sort of the answer to Andrew. They've got a biased, closed mind about things. The working physicists, they've been taught their physics education. They've done their degree, BSc, honours, and their MSc, masters, and then they go their PhD, and it's all being censored as to what they think they should teach them, and they've missed out a great deal of the history of all these sort of what are to them now discarded ideas, and so they don't really have a full proper understanding of Newtonian physics. They've just left it to be dealt with by the historians of physics, and they ignore it.
Well, that happens in general. Well, I'm still not quite sure what an atom has to do with, say, dark matter.
Well, you're talking. You go back to the 19th century. This is before they discovered the electron and all that sort of thing. So they were thinking in terms of the small particles being spinning around like vortices.
Yeah, although I would have to say that the least favorite physics concept that I have is the vortex, and that atoms made out of vortexes is probably my least favorite conceptions.
That's why it's not very nice. I don't like it. It's sort of when the math gets into that area, it gets too hard, and that's one of the main reasons why the idea was abandoned. The mathematics got too hard. If you go through that paper, I think it says the mathematics got too hard on this vortex theory. But the things you deal with it came out of it was things like not K with the K, that is KNOT. So you've got in the mathematics you've got knot theory, and knot theory is still being used, and it's still being used in things like superstring theory. So a lot of the mathematics that was being used in this vortex theory has now been used elsewhere in other theories, but in the context of Newtonian physics, which led to the idea of the unified theory as being the vortex theory. That the physicists have just ignored that, left it to the historians.
Well, I don't know. I think that should have been ignored. But anyway, so Robert K has this thing about explain why some galaxies have stars rotating faster in the outer shells than what Newtonian gravity predicts. Well, of course, that is the entire theme of this presentation. And if you don't get that, then you're not getting anything. So I think I have to go and address this again. And the question is, what do you mean by what Newtonian gravity predicts? Okay, so this is the key question. The key question is, how do you calculate what the Newtonian gravity predicts? Now, if you use the presumption that gravity is 1 over r squared, then you get the expected decreasing curve that we see in that very typical dark matter picture. Now, however, that particular picture presumes that all the matter in that galaxy is concentrated in a speck in the center of the galaxy. And that's why the force of gravity decreases the further you go out. And so you would expect the stars on the outer to decrease. So how do I explain why that doesn't happen? I explain that because all of the matter is not concentrated in a speck in the middle of the galaxy, as the 1 over r squared gravity law would presume. You've got instead all of this mass, which is distributed evenly. If you look at a galaxy, it's bright, not just in the center, but all around. You've got all this mass that's toward the outside of these stars in these outer shells, right? And so you've got all that mass. The further you go out, the more mass you are including. So you would actually think that the gravity as you go further out would actually increase. And so you would expect that the stars on the outside would actually even go faster. And that is actually what we observe in that typical dark matter picture, where you can see that the star velocity actually increases the further you go out. So why is that? Because the further you go out, the more mass is inside the orbit of the star. The more mass is in this orbit of the star, the more gravity. So that would explain, you would expect there to be more speed, more velocity. So hopefully that explains that problem. So I was wondering, Harry, so are you back now that you've turned off your camera? Do you have enough bandwidth that you can speak without being interrupted? Are you there, Harry?
Well, I don't understand your last explanation. I don't understand your last explanation. How is it that the speed is faster the further out? And
well, you would agree,
I didn't really understand that.
You would agree, Harry.
You've said that a couple of times, and every time you say it, I don't understand it.
Okay, so let's go back to say this typical picture. I'm going to share my screen. We're going to share just my presentation. Okay, so we have this typical picture, right, Harry? Do you see that?
Yes, I see it.
Okay, so we have a galaxy here. So it's got a central disk here. And you can imagine there's like a certain
what galaxy is that? What galaxy is that?
This is M33. And you can
say
M33,
okay.
Let's say there's like, just for argument's sake, a million solar masses contained in just the central bulge, right? Now, as you go out, further out, let's say, let's break this, we can, let's break the visible part into here into like, you know, at least 3 segments. So as you go out to like the first third, you can see that there is more mass included inside of that 1/3 ring. So if there were 100 solar mass, you know, what did I say, 1,000 solar masses in the central bulge going out one rung out, you know, there might be the same amount of mass in that outer ring. So now we're like at, you know, 2,000 solar masses as we go 1/3 of the way out. As we go a third, even like a third ring out, it being included inside of that ring might be, you know, 3,000 solar masses. So the further we go out into the galaxy, the more and more mass is included inside the radius. So you would agree with that? The further you go out in this galaxy, the mass inside the orbit of any star increases, right? Would you agree with that? It's important that you understand that.
Well, that's your hypothesis. So I don't understand. You're saying the gravity is stronger or weaker. I don't understand what you're saying.
Well, it obviously gets stronger.
You kind of stick it. The 1/4 law doesn't depend on how much mass is there. It just means that it doesn't change the doesn't change the calculation as far as I can see, as far as disproving or proving this thesis.
Well, the thing is that you can't. Well, I'm trying to prove it in the sense that you can see that as you go further out into the outskirts of the galaxies, that there's more mass inside the radius, right? That means there's more gravity inside the radius. I mean, even if you presume that, because this is what people do, is that they presume that even using 1/r² gravity, that you can treat all of the mass within a certain radius as being all concentrated in the center, right? Even if you assume that, then as you walk further out into this galaxy, you would see an increasing amount of matter. Do you agree with that? That's an important point.
So you're trying to argue that there would be more matter concentrated at the center as far as doing the calculation for 1/r²? Is that your thesis?
Yes, even for the purposes of that calculation, you would have to say that the amount of matter that you're concentrating in the center here, like let's say there's 1,000 solar masses in the center. Out here, you would have to say there are 3,000 solar masses.
Yeah, but I don't understand how that. What does that have to do with your thesis? You just seem to be waving hands now. I don't understand.
If there's more mass out here, that means that this star has got to go faster. It's got to
but
go.
all the stars would go faster relative to the one that you're referring to because they're all going faster now. So that doesn't really change anything as far as I can see.
Well, what would you predict would be the velocity of a star, say 1/3 of the way in the galaxy, and it's exposed to 1,000 solar masses, and then you go like 2/3 of the way out in the galaxy, and it's exposed to 3,000 solar masses. Then you would expect.
Well, I'm assuming that astronomers know how to do these calculations and they've done them correctly. So I'm not sure I understand why there's an issue that you claim is wrong.
Well, the thing is that they've not done the calculation correctly. That's my entire point. That they've done the calculation.
So your claim is that the discrepancy is due to the fact that physicists and astronomers can't do calculations correctly.
That's right. They cannot do they're presuming that this flat disk galaxy is a sphere. That's what they're doing. And this is why
Well,
it doesn't work on
I don't. That's
the,
another part I don't understand. How are you claiming that?
well, I'm claiming that because I found these spherical galaxies which apparently have no dark matter. That's a big piece of evidence.
Yeah, but the fact that they apparently have no dark matter because the calculations work with those galaxies, so they are able to calculate the gravity correctly. And so then they say there's no dark matter because we can calculate gravity correctly. But when they can't calculate gravity correctly, they say there's dark matter.
Yes, that's what they do. But that also means that there could be a problem with the way they are calculating the dark matter. If it happens that this only works with just the spherical shaped galaxy, that it has to do with the geometry of the galaxy, right?
Well, don't you think that they would have taken that into account in their calculations?
Well, you'd think, but no, I'm saying that they haven't.
Okay, so your thesis is that they're doing the calculations wrong.
Yes, and that's also based on the fact that other people who agree with this hypothesis, like I said, this is not my hypothesis. I didn't come up with this. Other people have mentioned this in several other papers, and when they do their Newtonian calculations, which explicitly acknowledge that we're working on a disk and we have to break it up into little pieces and we have to integrate every single piece, like you explained with the pyramid, that they recover the observed rotation curve, right? So that's really good evidence that everyone else is doing it wrong.
Okay, so this doesn't really disprove the existence or non-existence of dark matter. It just shows that astronomers are doing the calculations wrong.
Yes, that really just shows that if you do the calculations correctly, as these other researchers have done, that there's no problem with just regular Newtonian gravity. Regular Newtonian gravity works perfectly fine if you apply it correctly.
Okay, so this doesn't tell us anything about whether dark matter exists or doesn't exist then. It just tells us that they made a mistake doing this particular calculation.
At most, it would say that this is not evidence for dark matter. It doesn't say whether dark matter exists or not exists. It's just, it's not.
Well, there's other evidence that they would claim there's other lines of evidence. And so removing this one piece doesn't really take away the evidence for dark matter. It just means that this one particular piece of evidence no longer is in favor of dark matter.
Yes, that's exactly correct. Yes. Because I had mentioned the other major lines of evidence for dark matter, which is, first of all, there's a whole lambda cold dark matter cosmology thing that relies on dark matter. We've got the bullet cluster with its gravitational lensing. And we've also got the cosmic background radiation power spectrum, which are all evidence of dark matter.
Well, imputed evidence of dark matter.
Yes, reputed evidence of dark matter.
Can I bring up a point which Harry dealt with? Can you put my presentation, another slide up, please? Why not?
Let's see, you got something else up here, Roger?
Yeah, bring up one. This is what Harry was pointing out about the dark matter with the Milky Way. And the title of this thing is something fishy happening with the Milky Way dark matter halo. So they are having a problem trying to understand dark matter in the context of the Milky Way. And if you're reading further on down to it, they're saying there's a problem with trying to measure the rotation of the galaxy when you're inside the galaxy, because the other galaxies, they're measuring the rotation while they're outside our galaxy, and you can see better their rotation. So they have difficulty trying to work out properly the rotation because we're inside the galaxy.
Yeah, that could
So
be
there
the
is
whole
problem there as
gravity
well.
works differently from the inside versus outside
That's
the
it.
gravity mass. Another interesting point about the dark matter halo is that they always say it is spherical,
Yeah.
which is kind of curious. You'd think that if dark matter was a thing, that it would be concentrated right alongside the stars that it's associated with. But from what I can read, you know, it makes the calculations a lot easier if it's spherical, because apparently that's the one place where the 1/r² gravity works. It's spherical distributions. So I mean, I don't know this, but for a fact, but I kind of suspect the reason why the dark matter halos are spherical is, once again, in tribute to them thinking that only gravity is 1/r², and they can treat it as if all the matter was concentrated in the center. That just makes it a lot easier for them to calculate, right?
So, yeah. If I read it out here, that stars have been caught crawling around the outskirts of the Milky Way more sluggish than expected. Slow motion, that scientists say, can only be explained if our dark matter galaxy map is wrong. And that's for our Milky Way galaxy. So they're having problems trying to fit dark matter into our Milky Way. So there's still ongoing problems. That these astrophysicists are having their problems.
Yeah, and I'm betting that if they were to try and plot the expected velocity of these stars,
Mm-hmm.
and if they actually integrated it by looking at every single star in the Milky Way galaxy against every other star, or at least tried to break it up into blocks, that they would find that the stars are moving at exactly the expected speed. That would be my prediction. Rather than using whatever they are using, the key, as Stephen Gift is trying to get to, was like, what algorithm are they using to come up with their Newtonian gravity? And like I said, it's some super complex integration that is very hard to fathom. Let me see if I can show you, what I found there.
Stop screen. Right.
So this is my document where I'm collected all of say my notes about this thing. Okay, so they use something called rot mod in Gypsy, which it applies a method described by Karen Sato, 1983. So, this is what me trying to find out exactly how they come up with this red expected curve here, right? So that's the curve that's in the document, that's in that typical picture for M33. And they say they use this thing, and the formula they use is this integral here, which I cannot say. It's not really telling me how they're calculating the velocity. It depends on this complex integration. Is how they're doing it. So that's as close as I can come to figuring out where they're getting these, curves from. But whenever you see something that looks like this GM divided by H, this is using the spherical gravity law. So anytime you see anyone calculating velocity like this, the only way you can do that is if the system is spherically symmetric. And so that would not apply to like pyramids or disks or squares or cubes. It only applies to spherical gravity, but yet this is what they're using, right? Right there. That's what they're using. They're using that. And yeah, this is what happens if you calculate the rotational curve for just a uniform thin disk galaxy. The further you go out, the speed would increase. You would expect that because there's simply more mass underneath any given star as the further you go out.
Yes, but the density goes down the further you go out.
Yes, but even though it goes
So
down,
the mass
it still
is
means
decreasing as you go out further because the density is decreasing.
no, see, that's a misconception because as the further you go out, even though the density is decreasing, that still means there's still more mass underneath that star. No matter how much it decreases, the further you go out, it's more and more and more mass. So you seem to be under the impression that the further you go out, the less and less mass. No, the further you go out, you're always including more mass. Every step out that you go out into the galaxy, there's more mass underneath you.
More mass that you're I just don't understand what you're saying, Franklin. I mean, it doesn't make any sense to me what you're saying. I mean, you're saying in effect basically that they use some integral that you don't understand, but they're wrong and you're right because the mass increases as you go further out. But they have an integral that they're using, and you disagree with that, and so I don't really see I can accept what you're saying.
See, once again, the integral is a shortcut, and because you know the way to do this correctly is to break it up into blocks and calculate each little segment.
Well, I think you need to go and look to see whether that's been done correctly or not, and it doesn't look to me like you've done that.
Well, the thing is that people have done it because, like I said, the math is, and I tried looking at that, but I only have so much time to investigate these things. But the people who have done the calculations, who do claim this as well, like I said, this is not my idea. Other people agree with this particular viewpoint that when they calculate it using individual blocks, that they are able to recover the galaxy rotation curve, right? So I don't have to do it. Someone else has already done that for like 47 galaxies at least, and it worked out perfectly.
Well, it seems to me like you should be showing us their papers and doing an explanation of what these people have done in their papers.
Yes, well, certainly we have some of that, like right here. Like I just found this paper today, and this paper.
Well, why don't you look at this a little more closely and look at whether or not you think these papers have did the calculation correctly or not?
Well, yes, I have, and I think they do. They explain that.
Well, you just said you looked at it today. How could you, if you just looked at it recently, how could you have done a thorough investigation?
Well, because you can read it. I mean, you can see it even in the abstract. That there's they're explaining that there's no empirical evidence for dark matter, and with that they demonstrate that the expectation of the Keplerian fall off is incorrect, and that a large number of mass distribution profiles should in fact produce an accelerating rotation curve similar to those observed in reality. And they go and they model this stuff.
What equations are they using? What model are they using?
Well, they did it by taking a picture of the galaxy and breaking it up into little squares, and then calculating, setting a matrix resolution at 41 by 41 and allows an approximation of the integral with blah, blah, blah. So they broke it up into a 41 by 41 matrix, calculated the mass on every little piece. And when they do that, they come up with matches that look like this.
What does the galaxy look like that they're breaking up into pieces?
Well, they would look like, this picture. This is like M101. This is NCG 9164. That's what they look like. And so they're able to get matches really good matches, right? And it's not like some straight, smooth line. When you actually try and plot the Newtonian gravity, you should get these squiggly lines, right? Which, because you can see like the arms and things in the structures of these galaxies. Whenever you see nice smooth line, you know they've ignored the entire contents of the galaxy and just like said, okay, it's all the mass is in the center in the point, right? That's their approximation, which is terribly wrong. So, you can look at these.
So what's who wrote this paper? I can't see on the screen here. It's too small to see.
Well, this is Konstantin Pavlov, June 19, 2014. Some guy. So this guy could be a dissident.
Is this a peer-reviewed paper?
No, I don't think it is. This is in it's Arvix. Yes. See, so not peer-reviewed. But of course, no peer-reviewed paper would accept
Okay, all right.
would accept anything denying dark matter, which would of course be the problem. But the fact that he was able to make the legit calculations, explain how he did it by like breaking it up in this 41 by 41 resolution.
What's this? There looks like there are two curves here. There's a curve here that looks like an exponential decreasing to zero. And what's this?
Well, right now I'm showing the pictures of the galaxy, so I'm not sure what.
I'm not seeing any pictures of galaxies.
You're not? Let's see here. What am I showing?
No, I'm seeing 6 figures that show rotation curves.
Oh, okay. Let me show you. I have to share. Sorry about that. Let me show you. I was trying to share the actual paper here. So let's see. Where's my StreamYard again? Present share screen. Why isn't that showing that? I have to move this tab to a new window. Okay, there. Okay, now can you see the original paper here? Newtonian explanation of galaxy rotation curves based on distribution of baryonic matter.
Yes.
Okay.
Looks like there are 3 authors.
Yeah, looks like there's 3 authors.
This is June 9, 2014. Is that right? 2014, so it's 10 years old.
Oh yeah,
Okay.
a long time. So this idea has been out there for a long time. But I'm just kind of hoping that with the new evidence against dark matter, that maybe people will start paying attention to this more, right? Because now we have
new evidence against dark matter.
Well, first of all, the existence of spherical galaxies that have no dark matter. There is no way they can explain how those.
Well, that's not new particularly.
Those galaxies.
Okay, scroll on down.
And the other evidence is that the rotation curves are flat out to infinity. So this is the picture I was trying to tell you about, and that they take a picture of a spiral galaxy, they put a 41 by 41 grid on top of it, and then they integrate the mass that's down in each one of those squares. That's the proper way to do the calculation. Any kind of calculation where you're doing it by just some formula, not looking at the actual pixels.
So just so that I can interrupt here, they're making the assumption that the white part of the galaxy represents a certain amount of mass. So they're assuming a relation, what's called a mass to luminosity ratio.
Yeah, that's typically how it's done.
Because they assign a certain amount of mass for a given amount of brightness in the galaxy. Does that sound correct?
Yeah, that's the way it's done, and that's the way everybody does it.
Mass density model setup. Okay, well, this this might be interesting for people to look at.
Yeah, it's certainly interesting. So,
Okay, let's go down to the curve.
so
Oh,
this
you
is
passed the
the
curve.
model.
Let's go up higher. All right, what's okay, all right.
Yeah, I'm not exactly 100% sure what they're trying to show here.
Well, they're saying that the curves change with respect to the density profile.
And if the density is very low, what were they saying about that situation?
I'm not really sure. This is why I said that you need to read the paper pretty carefully and go over it and understand what it's saying. So this is pretty good. So now we're looking at what the claim is, and
Yeah,
they're
it's like,
getting different rotation curves.
yeah, so they're
All right. Well,
plotting,
this is pretty interesting.
they're plotting mass density distribution, the expected circular velocity, which is their red line, and then the blue dots are the observed circular velocity. So their red line is right on top of the observed items here. And this is kind of what I would expect. And this is the biggest frustration, in that in these mainstream papers, they really don't plot what the expected circular velocity would be. And you would expect it to be something bumpy like this, right? But typically they're nice, smooth curves, which tells me that they're not actually looking at the galaxy for some reason.
Well, yeah, I can't fault you on that. This looks like M101 here.
Yeah, M101.
Yeah, it is M101. Now you notice that it's not really clear that these areas where it's dark, that's not really where there's not any mass or stars. That's just an area where it's obscured, and so that would be a fault in their analysis, because they're essentially only counting the bright areas and assuming the dark areas is an absence of matter, but that's not really the case.
Although that's curious, because I was trying to look up the reference saying that you can calculate the rotational curves from just the visible glowing matter, right? That, I think that was the claim, that just looking at the hot stuff, you can calculate by whichever way, hook or crook, the observed galaxy rotation curves, which would be another nail in the
Well,
dark.
they're probably accounting for what I just said about the obscuration. So I can see there's lots of obscuration, dust and dark clouds in there. I can see plenty of that. So
yeah, but you can kind of see how they're doing it. They're breaking it up in these individual blocks, which is the way I think you'd have to do it. Like if you go look in the mainstream papers, there's no analysis like this.
well, the question though then also comes in: what are they assuming for thickness? So you have to have some assumption about the thickness of it. I'm not really sure what assumptions they're using there. So that's a detail that you'd have to look at. All right. Well, I'm not sure we're boring people with this conversation, but this is a lot more specific than what I was led to believe initially. I mean, this looks like they did a pretty thorough job.
Yeah, they did do a pretty thorough job. So I was, interested to find this paper, although I was looking for that one reference saying that you can just look at the visible matter and you can predict the observed rotation curves from just that. If that were true, and you can just kind of even ignore all the other matter that's not glowing, then that would be another nail in dark matter's coffin, in that it's not really necessary. That if you can calculate just by looking at the visible stuff, whichever way they're going.
Well, here's the problem. The issue is this is a problem that existed. It's known as the missing mass problem, and it existed for many years. The actual dark matter, they never used the term dark matter prior to about 1980. All right, that was never used. They referred to this problem, this particular problem, as the missing mass problem. What happened was that the particle physicists Abdus Salam and Glashow and Weinberg and these guys had done their unification of grand unification and created this grand unification. And this was done finished towards the end of the 1970s. And what happened was they decided to get into cosmology. Okay, so they were going to apply their grand unified particle physics theory to cosmology. And that's when the dark matter comes in, because the dark matter is needed to make their cosmological theories work. And so the dark matter, if you do away with it, then their cosmological theories fall apart and disappear. And I doubt that they're going to let you do that.
Well, that's why we have to have all this actual new evidence that contradicts dark matter. That's going to force them into that corner. Then they'll be forced to look at these other alternatives.
I'm not really sure that would be the case, but I mean, as Roger likes to point out, they just do ad hocs.
Yeah, but they're in a real pickle with the existence of the galaxies, which do not have dark matter in them. That's a real pickle for them.
The way they're thinking is they've got their what we call paradigm, which is Einstein and relativity and quantum physics and all the rest of it, and they're looking for add-ons to that.
Well, the other problem is that they've had their chance. They've literally searched every single place that dark matter could be hiding and come up empty, right? There's been so many experiments looking in so many ways that in itself is evidence against dark matter now, right? You think if they had...
Well, I think it's primarily evidence against the idea that the dark matter is some kind of unknown particle that fits into the standard model of particle physics. And it doesn't. There's no way there's no dark matter particle out there that fits in. They haven't been able to find it.
Yeah, they haven't been able to find it.
I think one of the things that David Hilster complains about is going from special relativity. You have this sort of like missing energy problem, and they solved it by postulating the neutrino, and that was supposed to account for the missing energy. So they're quite prepared to do add-ons to their theory all the time. So if they got dark matter, they can't explain it. They're going to try to put another particle on to explain that.
Well, in effect, basically, it's cold dark matter and not hot dark matter. And the reason it's cold dark matter is because cold dark matter doesn't work out in their theory. So there you have a dark matter add-on, but then you have a second level of, is it hot or is it cold? And it has to be cold. So, I mean, it just seems more, that does seem a little ad hoc to me.
So if it's cold, it's not really going to emit much heat radiation. So that's another problem with trying to detect it.
Well, the point is that the cold part, I think, has to do with they need it to be cold in order for galaxies to form, because if it's hot, it can't condense to form galaxies. So it has to be cold enough to allow gravity to cause it to contract.
Yeah, that's why they need dark matter for actually any galaxy to form. So to have a galaxy that doesn't have any dark matter in it seems completely absurd. But it looks like we have come to the end of our 2 hours here. Yeah. So I'm just going to wrap it up here. And, try and, acknowledge, first of all, yes, it seems crazy that, 10,000 astrophysicists could be wrong about this, because that is the number one objection you'll get about this particular hypothesis that the gravity has been calculated wrong. It's like, well, 10,000 astrophysicists going to not be wrong. But in fact, I think they are. And I think they're going to get backed into a corner here with this additional evidence of spherical galaxies that don't have dark matter, and these other evidences of dark matter cannot explain the outside flat rotation curves for galaxies. So we'll have to start looking at these other people and papers which say that you can just properly apply Newtonian gravity, and then you can recover the curves, and then they can go fight over all the other evidences for dark matter, which I am personally extremely skeptical of, and I hope someday will go away. But so that would be my conclusion, and I thank everyone for participating and for Roger moderating the session. All right.
Thank you.